Let's see.
Yeah, I'm just literally on my paper, I'm just gonna write what pressure.
So this probably gonna make on like on Thursday, because it's like because we lost a day, and then next week, and then Thanksgiving. Somehow that will work out, I think.
Okay.
Anyway, we haven't covered this stuff yet, so it's kind of, I don't know, but we'll see how that works. But it's easier when you got like a weekend, you know? But it's this guy. So should have put these two earlier on, but I think people didn't see those two papers. Yeah, it would have been nice if they put the holiday today instead of like Tuesday. Didn't make sense. I don't know why they did it that way.
Voting day. That was a voting day.
Oh, for voting?
Yeah, on Tuesday.
Yeah.
So I think they saw that as a reasonable. Give people time off to go vote.
Well, everything won, I guess. It was worth it. Pot's legal now. Was it immediate, the pot thing? Or?
I don't know how it works. I don't know both out of state.
Okay.
I know when they, cause I'm from Connecticut, so when they passed it in Connecticut, it
Mhm.
was like a 3-month period afterwards, then it started.
Oh,
So like it wasn't.
Oh, I
like
see.
immediate. Yeah,
All
they
right.
had to build up.
did
some
they
infrastructure.
do like, so I'm worried about the people that are in jail for pot, you know? Do they get out or something? Or anyway, it's said, right? This one was really well specified, actually. Well, it must be in there about people in jail. I know people in Texas, it's like for just minor pot stuff, they're in prison for life or something, you know, 10, 20 years.
It's a hefty.
Yeah, it's crazy.
I'll be dead one day.
Yeah.
I was in Texas.
I mean, where are you from in Connecticut?
Just north of Hartford.
Oh, all right. I mean, I was born in Springfield.
Sort of Mass.
Yeah.
Okay.
Yeah. And I went to school at UMass, so it's not far from there.
Yeah, I was born in Windsor,
Okay.
and then I went to University of Connecticut for undergrad.
Oh yeah. Windsor Locks. So
Where the airport is.
Oh yeah. Oh yeah, that's right. Yeah.
And then Windsor's like right below it.
Oh, okay. So Windsor Locks is different than Windsor, huh?
Yeah.
Like I guess I've heard of both, but I always thought it was the same place. But yeah, I grew up in Rhode Island after that, so I'm kind of you're halfway in between where I was born and where I grew up.
Yeah.
But, did you do materials there?
Yeah, I didn't do.
Oh, okay. That knows. I mean, well, the Palmer guys have moved on, you know, like Corberstein was there and he went to Columbia after. I guess he was the main person I knew there, but then they've gone through a few people.
When I was there, it was mostly young faculty.
Yeah, it's a funny program, right? So they have an undergrad degree. How many students do they have?
Only 30 for graduating class.
Oh, that's great.
It was pretty small number stuff.
No, but that's pretty big for, because we were doing it. We were running like 15, and then it went down to like, and we had like 30 faculty and 15 students, 15 undergrads, you know. Actually, we had 20, high 20s, like 28 faculty. Yeah, and we had like 15. So then they pulled the plug on the undergrad program. I mean, it went down, and we were going to like high schools to try to get people to come in, you know, and it didn't help any.
Yeah, UConn would, so they offered in-state tuition to like the.
Oh yeah, because none of the
other
other schools have materials. Huh?
Yeah, so that would bring more people.
Yeah, because UMass doesn't. I mean, they have the Palmer program. They don't have materials at all. I don't think any other schools have it either.
So it pulled a lot of those.
Yeah.
That's how it worked.
Yeah, neither do the Ivy League or anything. I mean, MIT has it, but I don't think the others have it, like BU or any place. That's pretty interesting. Yeah, but it's not it's like a mixture department, right? So it's got like, it's not a formalized department somehow, right? The people have their tenure in different programs, I think. Like chemical engineering or chemistry or like biochemistry or something.
Yeah.
There seem to be a lot of people in biomedical there.
Yeah, the brand new building that they just built for the biometrics.
Yeah, it's kind of interesting. I mean, we're in some ways we're going down that road, you know. I mean, here, but it's not as effectively. Well, we don't have the draw. Like you would be like basically the only school in that, yeah, that whole part of the country. I mean, Stony Brook has it in Long Island.
Yeah.
And like RPI. But other than that, that's the only place for undergrad degree. But the employment was pretty good for the people leaving, like when they finished.
Yeah. Yeah. Everyone's spread out, but everyone found jobs.
Because we were like great, like we were getting like 4 offers because we did co-op too. So they got where they worked, and they get like 3 others.
Yeah.
But we were graduating like 10 kids. There's so much demand, and they were all right. All of our kids were on full scholarship from the department.
Wow.
Yeah, it was insane, right? We couldn't recruit anybody. We couldn't get anyone to come. You know, it was totally insane. Guaranteed co-op job at a good place. Full scholarship.
Amazing.
Yeah, and they just closed the program because we couldn't get anybody. And we were begging people who were going to high schools, like, please, you know, here's $20, you know, just apply. I mean, it was pretty crazy. Maybe it'll come back, I don't know. But all right, so anyway, so I had to go through this thing. It's pretty tough. Like, it's not that easy. But there aren't necessarily answers to the things. That's what makes it even kind of harder. But this one everyone got, like, just what is kind of what is Brillion and Raman scattering. Oh, so there's a tour today, so at 3. Is anyone going to make it for that? Or hopefully there's more than like 2 would be good, you know. We get 2 people, it'll be pretty decent, but because he's setting up an experiment and everything, I think. Like I asked him if it was still on, he was like, yeah, we're all set, you know, the machine's warming up and all this stuff. So hopefully someone will come. I mean,
what room is this in again?
All right, I don't know the number, but you know where the world is?
Yeah.
Like, so that's 413. So if you keep walking straight and the bathrooms are on the right and just straight on, it's right there. So
20 minutes or so.
yeah, it probably won't take too long. It's just like see what he's doing. Anyway, we did a homework on, you know, it's not that important, I guess, but basically we did a homework on it, and I just see, and there's one down there.
Okay.
Like that, like I said, there's not many of those around, so it's kind of like we have one. So, and he's pretty proud of it, and it's like he could also talk about dynamic neutron scattering and stuff. Like he was at Oak Ridge, you know, so he does like biomembranes and how they vibrate, looking at the water in motion, the membranes and things. Anyway, so yeah, so that everyone did okay on that thing. And then so this thing, equation 2 is this kind of crazy equation. It doesn't seem to come from anywhere, and it's not in any of the books, you know. That's a weird thing about it. So, but if you so you had to go to the to figure this out, you had to go you had to go to these papers that were donated here. So this wherever it is. So this reference 13 gives an overview, and then this thing gives the details. So the last two papers are where the action is. So the question is like, where did he get, like, what does this thing come from? And then this thing looks like you have the adiabatic compressibility, and they have the heat capacity, CP. Then like those those both come from this DH dt expansion in terms of entropy and pressure. So you can get that term and that like 1 over CP, and actually it's 1 over beta S and CP is what you'd get if you did that DH dt expansion. So you'd get made that kind of been in class, right? You do anyway, a couple people did that. You know, there's different things you can do. Like you do DH, like so you have DH is VDP and then TDS. Right, and then you can do DH dt, and then DP dt a constant S, and DS dt a constant P. Right, and then you've broken this into a function of S and P. Like you've broken DH into S and P. And the paper he talks about doing d eta, which is the same as d chi. So this is like if you put a field on, and then out of the and you have some kind of object or a molecule, and then the electrons are going to go with the field. They'll oscillate. If it's an oscillating field, like an EM field, then it's going to oscillate, right? So the susceptibility is how susceptible is it to that oscillation from a field. Susceptibility to an electric field for the electrons to move around. Anyway, the same thing in the paper he uses this eta. It's the same thing. So you can write that in terms of P and T, and that was done by Einstein according to this paper. And then our friend Landau and some other guy, P something, figured out that you could do it in terms of S and P, which is kind of what's done in the equation, whatever, right? So anyway, so it's pretty complicated, right? It's not simple. So or S and P, and then P you can convert to rho, to density. So you could just go, like if you did that, that was pretty good. Like if you did broke down how that DH dt can give you, like one of the terms is directly the heat capacity, and the other one you have to do the triple is it the triple, not the, yeah, the triple product rule. And then you can convert that to the beta sub S. So it was kind of like asking you to do the first couple classes, we did that derivative business. So you could, no, I think one group did that. So there's various ways you kind of skin the cat here. You know, I mean, there isn't one that's very rewarding, you know, like where did this come from? Anyway, so you can, this is the book. What, I'm forgetting your name. What is your name again? Bill. Yeah. Yeah, William got this. He got this and he got this thing. So he like saved the day, but no one picked up on it. Did your group use this, or?
It was, I didn't do that, really contribute to that question, but.
Yeah, so you guys saved the day, but there's a lifesaver floating there in the water that you got, but your guy's drowning next to you. No one said, like, you know, there's a lifesaver there.
That was the third group partner.
Anyway, whatever. It doesn't really matter much, but basically the answer is here. So he says like that this term, so if you think about it, when the let's see, So say the electrons are just shuffling back and forth, right? And it's the same frequency as a wave that came in. There's no vibrations or anything. Then you think about it, it's like you're kind of ordering the electrons. In other words, when they cluster, they're more ordered than when they're dispersed, right? So that's an entropic thing that's going on. That kind of elastic response to the electric field is going to generate the Rayleigh central peak. There's an elastic response to the electrons. Okay, so that's entropy changing. So that would be the pressure term. That's this guy. And the adiabatic term is the other thing, like you're going to be putting in a pressure differential on it, and that changes the electron. In other words, they're already vibrating from the second term, and then they add in this vibration from the pressure field, the sound field in this crystal. And that's the first term. So he kind of says that here. And he also says, like, to get that other paper that Bill got, or William. Do you go by William or Bill?
I go by Bill. But
Okay.
yeah.
All right. So anyway. So then you could go to that other paper where this thing is exactly spelled out, and he goes through the brutal history of it. So this is actually kind of interesting if you're interested in this, Like he goes through. So you had to kind of really read this. So nobody found this. It was on the page, but so Einstein said that you could break apart this susceptibility in terms of density and temperature. So in other words, so you take this thing and say, oh, it's made up of changes with density times a change in density, and then changes with temperature. That's a Taylor expansion, right? So you just expand it in terms of two parameters. So thermodynamics typically PVT, so if you have V and T, you get P. So you get two things and you get the other thing, right? So everything's like two parameter binary breakdown. So you're going to do this for everything, just break down into pick your two parameters, and then so this is like in the thermodynamic square, you had so basically volume is basically 1 over rho. So that's basically density, and he's saying volume and temperature. So you could do these two also. You could do S and P, or you do S and V and P and T. So you take kind of the corner thing's going to be where you do the derivative against. So anyway, so that's what Einstein did. He said you could break it down into that. Then he got an equation. So then because the square of that's going to give you the intensity, because it's basically a complex number. But you could think of it as plus and minus. You're going to get plus intensity. You get like intensity is not going to suck light away. So it has to be a square, right? So, but it's also a complex number. Some groups said that. That's true. Anyway, so you're going to look at the square, and that's how the intensity that you're looking at is going to be related to that square differential. And here's the differential with the density wave. This is d rho. The rho is erased in this. Like every time, like here, somehow maybe this was when they first. This is 1966, so they just invented typesetting, and they hadn't figured out how to do rows like that somehow. But anyway, so we got that business. So basically intensity is going to be the square of this thing. So you have the square of that, and then it's going to be the square of the differential. So also they couldn't figure out how to put the superscript above. So maybe this is actually an error in the typesetting. It shouldn't be t squared. It should be dEd rho sub t, like t held constant squared, times del rho squared. And you can there's no cross term. Like normally you'd expect to be dEd rho squared, and then a cross term del t times del rho. That's missing because Einstein said rho and t are statistically independent. So you don't have a cross term, so you just have those two terms come out. That's why our equation also has just two terms, right? So you can solve that. So Einstein said one of these two, the Rayleigh one, isn't important, and he just solved it for the Brillouin scattering part, right? And he got an equation for it in terms of this beta t, which is a normal isothermal compressibility. That's the normal number used for change in volume of pressure. That's a normal number. Anyway, so that's good. Then there were some problems with that. It didn't exactly predict the right I by I naught So the incident intensity versus the scattered intensity, somehow it didn't work in terms of trying to figure out what the ratio between the Brillouin and the Rayleigh scattering was going to be. So the I always pronounce this wrong. The B scattering and the Rayleigh scattering is a C. The ratio is the heat capacity. So that was someone, I guess Landau did that too, but that's going to be related to these compressibility terms. Anyway, so that's the idea, is like you're not getting the right number for that ratio between the Rayleigh and the Brillouin, right? And that's the number you can easily get if you do this measurement. You can easily get the ratio of those two intensities. This doesn't give you the right ratio. So the Einstein thing doesn't give you the right ratio. So Landau, like when in his spare time, I guess, so he did a lot of things, but in his spare time, he figured out this Brillouin intensity function. So it's the same crazy Russian guy that got in the car accident and said, like, if I had answered it correctly, I wouldn't be Landau. So anyway, so he figured out that instead you can just say ad hoc, like there's two parameters, you used rho and t, and I'm going to use S and P. Like I'm just going to break apart this susceptibility into those two. Then I'm going to square it, and then I'm going to just work out what those terms are. And that's it. I mean, he just worked it out, and then he got the right ratio for that I Brillouin. So if you had really wanted to do this ad nauseum, then you would just like go through exactly the steps that he does in this paper. He goes through every step of the differential. He breaks out, uses the triple product rule. He does some other things, typical like derivative of thermodynamic parameter kind of thing. And then he finally gets like our equation. The equation that's in that paper is this susceptibility with density squared, and then this beta S and the CP. He just gets it out. And then you could, I guess what I was expecting is you take that derivative of the heat of the enthalpy and then go back and say, like, there's these two parts, like an entropic and a thermal part, and somehow just say, like, qualitatively how that fits together, which wouldn't be an easy thing to do. And I'm not going to do it. But basically, that's what I was expecting. But you could have just gone through this paper. He does an exact derivation of it. Do the same thing. So anyway, most of you found an easier route and just kind of scrabbled through it somehow. So that's all right. Anyway, so this isn't, so he just plops this down and doesn't really say much about it. So it's kind of a weird thing. In fact, all the equations in here, he just plops down. And this isn't a conventional equation. If you look in those other, like there's two books here. There's this Raman scattering book and this other book, and neither one of those have this business in it. So he should have explained this better. Anyway, he didn't. Any questions on that thing? That's about all I have to say about it. It's quite a bit. But and figure 3, everyone got this thing. Everyone got that stuff. This thing everyone got too, the velocity. One way or another, everyone got that. I mean, it turns out you can get that equation 4 and 5, right? So that I hadn't really anticipated. You can get that from just the density of states equation for the Debye function, which has a sine theta in it, theta by 2 in it. So you can either get this by saying that that's the d-spacing, or you can get it by saying the density of states for Debye function. You get the same answer out. In fact, it's cleaner if you do it that way. That's a better way to do it. But and then this thing, some group like solved this thing exactly, so it was pretty good. And then I guess I had like a hand waving argument about that thing. So basically it's just like fishing around the equations. That's the point of this. Then full width at half max, glass and crystal. So this thing, let's see, I actually wrote some notes down on this business. This thing is there's a lot to this stuff, I mean, maybe I dwell on it too much, but so if you go like, I don't know, I found this thing today, but You find it. Anyway, when you have NMR, do an NMR pattern, you get these spikes, right? In other words, for each nuclear, so that you're looking at nuclear resonance and the radio wave comes in, it makes them precess. It means that they, under a really strong magnetic field, they normally they're flopping all over. Then like a guitar string that's not taut, then you put a huge magnetic field on it and they all go straight up, you know. And then at that point, it's like the guitar string that's tightened. And then you send in a radio wave and it's like blowing up a bomb next to the guitar string, it's going to vibrate, right? So basically they precess, they tilt, right? So, and you can do that in a solid state. You know, normally it's done a solution, you put your stuff into deuterated solvent, you do this measurement, you get the spikes for the different vibrations of the nuclei precessing. Anyway, so they have this issue of a broad peak and a narrow peak, and the narrow peak shows up for liquid, and the broad peak for crystals. What they say in NMR, there's a web page. I don't think I linked it, but what they say is that it's got to do with the anisotropy is locked in when you have a crystal, and because it's anisotropic and it's kind of like randomly arranged, that makes the peak broader. And when it's a liquid, all those anisotropies cancel each other and it makes the peak narrow. It sounds like something just pulled out of their hat. Like it doesn't sound like it's in exactly the same thing, except in early on it's talking about anharmonic and harmonic. Like we were looking at anharmonic effects and harmonic effects for the heat capacity. So they do the same argument and also kind of pulled out of the hat why the liquid one is sharper. So the liquid peak is sharper than so this is important to tell liquid from crystal, and these systems have really complicated crystals that are hard to, you can't exactly use diffraction to see it, but that way. So basically this is a way to observe whether your drug is going to work or not. And it's kind of one actual use of this technique that's going to have some value. This is for proteins, and they show the patterns here. So you can see like that one's pretty sharp and this thing's pretty broad. So basically the liquid has a sharper peak than the crystal, which doesn't make any sense normally. Like you expect in diffraction, perfect crystal is going to have a really sharp diffraction peak, and the liquid's going to have this amorphous halo. So from a diffraction perspective, it's the opposite of that. But from this kind of spectroscopy perspective, like NMR, that's exactly what you see. When you do solid state NMR on a liquid, you get perfect spike. When you do it on a crystal, you get these broad peaks. And from the breadth of the peaks, you tell about the associations between the atoms in the crystal, the nuclei in the crystal. So the same thing's kind of going on here, and the argument is the same thing. It's kind of like all the biases that are in the crystal part disappear when you go to the amorphous stuff, like a glass, because they're averaged out. The plus and minuses kill each other. So I'm still not really convinced that makes sense to me, but I think I'm coming from a diffraction perspective. So basically that's the argument that's made for this thing. You couldn't have really come up with that unless that's what I wanted you to get, but it was almost impossible to get that. So it doesn't really matter. Unless you said something like wrong in the answer, I didn't take points off. But if you said something just like crazy, then I took a couple points on this one. So that's about it for this. Not an easy homework, but I don't know. Hopefully it took you down some road that you looked at a few things and just kind of thought about them. That's the idea of it. Any questions on that thing? All right, good. So anyway, next week, Thursday, like instead of Monday, because it's like we're like a day off, plus like you don't get a weekend, so at least it's like a little bit more time. Like before class on Thursday, say, it'd be pretty good. And this one's also kind of difficult, I guess. It's basically like we're going to be going through mixing equations, and this is a mixing equation for things that interfaces. So I don't know, it's kind of just an example of those type things, so it should be okay. So this chapter in this book goes through some, so it's kind of a weird chapter. Like the book has already gone through like solution models, like basically the Hildebrand equation, right? So it makes you wonder like what else is there to say. So like the Hildebrand is pretty simple. So you just have this enthalpy and you have the entropy and that's it, right? So there's just one number for the enthalpy, and basically you can predict the phase diagram with that. So that's good, but there's a lot more complexities to deal with in systems, and people have thought about it quite a bit. So there's a lot of different kind of rabbit holes that people have gone down to describe mixing for systems where that simple model doesn't exactly work. And so that they can account for certain features that are important to them in different systems, like a lot of different systems, right? So anyway, that's what this chapter kind of has morphed into. Like he started it and he's got almost like a garbage can of stuff. And then I added more garbage to it. So it's kind of a bunch of things. But so he begins, like he had just finished doing heat capacity. So he's got the partition function. And he says, first thing in the chapter, he goes through like how you can use the partition function to get the mixing equation, like ideal mixing. He says like partition functions, some of these Boltzmann factors, and then the log of that's going to give you the energy, like the free energy of mixing, say, right? So, and then he needs to add something to this, that instead of just a sum over J, you can say a sum over states, and the states are degenerate, meaning that for one energy, you can have multiple states of that. He needs to add that because what he's talking about is this thing, which can have, so for this mixing situation, you could have many different, like if I swapped that gray one for that white one, well, it's the same mixing situation. So there's a lot of different degenerate states that are possible with the same amount of mixing, same state of mixing, right? So you need to have this degeneracy factor, and that degeneracy factor actually was already obtained to get this log x thing. It's this factor, right? And once you have that factor, so you have z as that factor, then exponential of u by kt. See, if you have the two things independent, so you have just the gray things and just the white things, ua and ub, say white and gray, right? The two energies isolated. So ua plus ub is the original state. So G minus UAUB is delta G of mixing. And then so the only thing, if you take a log of Z times KT, then this thing just becomes UAUB. And then this term becomes a dominant term. And this thing is the same thing we had before. Basically, use Stirling's law, Stirling's approximation for large N. And if you work through like ln of this thing minus log of that, you'll get basically the same thing we had before, like this mixing law, starting with the partition function. So it's kind of interesting that you can do that. It also opens up a different way to understand this. Like you can talk about different kinds of contributions to mixing. So it could be like a vibrational contribution to mixing, like a heat capacity thing. And you can add terms to this equation in cases where you'd see vibrational mixing of something, like two states. So this say instead of mixing balls, you were talking about mixing of magnetic moments in a magnet, like a Landau icing kind of model thing. And then you'd want to know about vibrations of those and how that contributes to the entropy to this term. So if you want to expand this beyond balls mixing, then it might be good to have a different perspective on it where you could include partition function to kind of understand it. So that's kind of what he's getting at here. And just as another way to derive it. So the entropy of mixing and this excess entropy, which is going to be basically, so that's the ideal solution. The regular solution is to add in the other one, and that's, we kind of already did, but basically talk about the kinds of enthalpic, so enthalpy is 0 here, or you could have enthalpic interactions like gray, gray, white, white, gray, white, There's three kinds of enthalpic interactions, so A, B, B. So in each site, like there's 6 sites for each one here. So if it's a cubic in 3D, it's 6 also, I guess. Oddly, the hexagonal one has 6, and also the cubic in 3D has 6. So Z is six types of associations. If you say that A is going to have, for each A atom, so you're going to have Z 6 bonds, and those are going to be made up of AA bonds and AB bonds. So it's going to be like for every AA is going to contribute 2 to, and this is 1, so that's kind of how this thing works out. So you get 1/2 Z. And so if you take that and do the same thing for NA, then you have Z 1/2 NA and B, and then add up NAA plus NBB. The 1/2's already over there, and then 1/2 NAB plus 1/2 NAB is NAB, and then you can get that this total energy is going to be. So then you can solve this for. So you can say, like, I have these energies UAA, UBB, UAB. So I'm going to get an average energy that's going to be UAB plus 1/2 of UAA plus UBB. That was the Hildebrandt thing. So that comes from this basically. So you're going to have use the number of AAs, which you can get from this equation, number of BBs from this equation, number of ABs. So basically the number of ABs falls out of this equation when you write AA and BB. So you're going to get A. So AA is going to be A's minus AB, A minus AB. And then B is B minus AB. And then you have AB times UAB. So the A's fall out, and the B's fall out, and the AB's fall out into this, and here's our average energy term, right? UAB minus 1/2 UAA UBB. So that becomes omega here. It can also be like caret energy, like average energy of interaction. And then these other ones, so that's average energy of interaction, and these two, what happens to those two? Let's see. That's our average energy of interaction. That's omega. Oh, and the other two are UA and UB. Those are the original mixtures. So you're saying U, so it's going to be delta U. So the UA, UB, this is UA, that's UB from the original. You'd have 1/2 A, 1/2 B. So that's UA, UB, and this is the mixing one, the omega thing, omega NAB. And then if you plug that in, so you have the multiplicity, or the multiplicity of the states times that energy over KT, and then this part gives you the same ln X ln X, XA ln XA, XB ln XB. This is the original one that gives you the delta G, subtract that out. Then you have this guy over here times omega. So this guy ends up being, so NA by N is XA, that's a mole fraction of A, and then B by N will be the mole fraction of B. So you end up with XA, XB out of this thing. And then omega, use omega, which is this average energy, Avogadro's number, and the Z, you pile those together into this thing. So it's a Flory-Huggins equation. You divide the whole thing by KT and say G by KT, and you put it divided by KT in here too. So the entropic term has no temperature. The enthalpic is 1/T for the Flory-Huggins. This is delta G over KT. Right, so it depends. The Hildebrandt does it this way. Flory-Huggins divides by T to make it kind of simpler to do derivatives. Anyway, so we already kind of went through that. And then we went through also, I mean, the difference here is that there's no difference for that part, the regular solution part, actually, except he gives a little bit more detail. The difference is that he started with the partition function to get this stuff, to get the ideal solution part. And then so anyway, so we got that business, and then you can get the chemical potential. This isn't, so it should be the chemical free energy per moles of A, not the mole fraction of A. And there's a difference, right? So, but anyway, generally people just say this. And if you say that, then you can say that the chemical potential difference, which is defined, that defines the activity coefficient. So if your omega is 0, then this activity coefficient is x, a mole fraction. If not, it's going to be related to this expression, and then that gives you that, and then the activity, then the gamma is activity, x times activity, x times gamma is activity, right? So this extra part, since the log of something times something is log of something plus log of something, then you get that this gamma is just that, which is the equation we had for gamma relates to xb squared, which gives you these kind of plots of. So if you have an ideal solution, so gamma ln of gamma is omega times xb squared, and if you have omega 0, then gamma's 1, right? Gamma would be 1. So let's see. Ln of gamma 0 is ln of 1 0, so it'd be 0 on a log scale. So if you have no interactions, that's 0. And if you increase the interactions, you have repulsive interactions. In other words, we have this equation, so you have this number is negative because ln of something smaller than 1 is negative. So that's all negative. That's the entropy of mixing. It drives mixing. And this guy would drive phase separation. So when these two balance, that's the phase separation point, the positive and the negative. Right? But if this is negative, then you just have miscible. Completely miscible. This negative plus negative means you've dropped the free energy on mixing. This is positive, then you get a transition point. Right? So this is like omega positive, where you're going to get a phase separation, and omega negative, where the thing would just be miscible all the time. Right? And then you can plot also. So you'll see plots on papers of ln gamma versus x. You'll see this plot a lot, so basically he's showing it here just to say, like, this is what it looks like, and then following the Hildebrand equation, and then because you can measure this gamma, and you can measure that, and you can plot it against x, and you get this plot. So then activity is just gamma times x. So if activity, if gamma's 1, if omega's 0 and gamma, so exponential 0 is 1, so gamma would be 1, then the a is x. So if you plot activity versus x, that would be a straight line, right? That would be just, they're the same. And then as you change the omega, you get these like deviations in it, in the activity. All right, so it's just kind of showing the general behavior of activity, gamma, omega, chemical potential, kind of the whole 9 yards of it. And we went through before this thing, like, so a thermal system would be, it's ideal. It's an ideal mixing system. So that's not the phase separation point, right? In other words, that's a miscible system because this is negative. If this is 0, it's athermal. There's no temperature dependence to delta G by T. In other words, this would be omega by T. So it's called an athermal system when that's 0. But it's not, it's a totally miscible system because entropy drives mixing. But the phase separation point is where this term equals that term, right? This is negative, that's positive. Then delta G goes to 0, that's the phase separation point. So you need to have a special omega to get phase separation. Right, like 2. 2 is the number here. So basically this goes flat, that's the critical point for the system. So this is totally flat. It means if you put something in here at some composition, then it fluctuates left and right. So there's no deciding point. So it can just fluctuate all the way over to here or over to there with no energy penalty. So wild fluctuations can happen with no consequence. It's like the Mardi Gras of the phase separation. Right? And then you get into, if you go to higher, then that phase separates into that phase and that phase. Right? The two minima in this thing. And then draw a line that's kind of the tie line for that thing. And then if you're down here, it's totally miscible. You have negative omega. So when you're 0, it's totally miscible. This is kind of like a catch-22 question. Like, I have an athermal system, omega 0, is it miscible or immiscible, or is it at the phase separation point? If you say it's at the phase separation point, that's not right. Right? No, you have to get some positive omega to overcome the entropy of mixing in order to get to the critical point. And the other question you can get from this is like, what's the problem with being at the critical point? And the answer is you can't tell any prediction at all. Thermodynamics becomes useless. Just throw away the book if you're at the critical point, because there's no rules applied. Anything can happen, right? So thermodynamics tells you anything can happen at the critical point. So they talk about critical slowing down. Like if you have phase separation, you want to drive phase separation, you go to the critical point, nothing happens. It's called critical slowing down. Like nothing happens there. There's no driving force. Anyway, so what is that business? So what else can you talk about here? There's a lot. Okay, I think there's like 60 slides of what you can talk about in this thing. Those 69 things you can talk about mixing. Okay, so it's not just that simple picture. So the first thing that people thought about so many different aspects of mixing, right? It's almost like, and everyone has a certain system they have in mind. So say this is our picture that we had with the marbles mixing, right? So, and then say you're going to go, say this is the picture you have. So you have something like oil and water. The oil like kind of collects along the surface of the water. It could be amoebas and something else. Could be anything, right? So basically, there's an entropy change here. Like this thing, the entropy changes that the blue mixed with the red, and that's combinatorial entropy. That's a mixing. It's like a mixing entropy, right? But here there's an organizational entropy, so it's not called a non-combinatorial entropy. So the things have organized. Yes, they mixed, you know. So if you looked at it here, then you looked at it there, this is pretty well distributed, you know. But basically, there's an organizational thing that happened too. Right, so that could be a big thing, since entropy only depends on numbers. It doesn't depend on mass, right? So the number of things that organize is a lot here, right? So that could be a huge free energy difference to have it organized like that. Anyway, so how do you deal with that? So basically, everyone wants to keep this thing because this is your favorite thing. Like everyone understands this X ln X. When they see that, they feel really warm inside. You know, that's like their thing, you know, whatever nursery rhyme thing that's like, and then this thing is added to accommodate this kind of mixing where you have interactions. So you want to bury everything into this term because you don't know what it is to begin with, this enthalpy term. Like basically you already feel not very, like after this big discussion about the energies and the average energy, it doesn't leave you warm and fuzzy. So basically just use that as a garbage can. So basically that's the approach that everyone uses. This is the garbage can of the mixing thing. You have something you feel very safe with, and this is everything else. So you're going to put this thing into that. So you say, okay, so the way this thing looks, when I don't divide by T, there's a T term here. That's how you distinguish between entropy and enthalpy. Enthalpy doesn't have a T dependence, and entropy does. In other words, temperature drives things to move, to distribute, to randomize. Temperature is randomizing the thing, so it's kind of like that's entropy. Like heat divided by T at least is the entropy, right? So T and entropy are kind of related to begin with, right? So if you're going to throw another term in here, and this is an organizational term, so it's going to be an entropic term, then you need to add a temperature term. You just say, so the way this works, this is negative, right? And this is positive. This drives mixing, this drives demixing. Then this entropy term you're adding is going to drive mixing. Like you're saying that this is mixing. Like when this thing attaches to that, that's mixed. And when it isn't attached to that, it's not mixed. So you're defining mixing that way. Then this is a negative term. So you have your positive kind of thing you can calculate energy, and you have this other eta thing that's just sitting here, right? Some other number that's entropic, so you throw in a T, and it's negative because you're saying that favors mixing. That's going to drop my free energy in the system, right? So this is a standard way to deal with things. I mean, it's the first step of, so you talk about like energy, and you say like, well, free energy is going to be delta H, like an enthalpic term, and then minus T delta S. So everything is going to be like this. When you try to complicate things, you're going to add in a negative T delta S to it. Like you have some kind of idea, you have an enthalpic thing, and you're going to add in this T delta S thing to it, right? Which immediately gives you a magic number, because you know when this thing is 0, you have an athermal system, right? And that's, or you could say when this thing equals the entropy term. either one, but basically usually say when this thing goes to 0, that's an athermal system, that's an ideal system. So I reach an ideal mixing system. So I can set that to 0 and I can solve for this eta, or more conveniently, I can solve for tau, which is a temperature. Like eta is a 1 over temperature. We can't say what that is, but tau is a critical temperature. It's where stuff happens. You might want to think about tau instead of eta. Tau is 1/eta, so you just say it's like that. You set that to 0, you find out that tau's the enthalpy that we had before, and then an entropy. So this is just like finding the equilibrium melting point. It's the same thing, right? We had delta G from melting for crystallization is delta H minus T delta S. If I'm at the melting point, delta G is 0. So the magic temperature where that happens is where delta H over delta S is that temperature. So I have delta H is this mixing guy. This is like the delta S for mixing that has to do with the organization of these things around the balls. Right? Then you get that magic. So this heat of fusion, this is heat of whatever. Heat of something happening, whatever it is, it's a critical temperature. Right? So this is like a common way to look at this. So in the book, they don't do it that way, they do it this way. He says, so he has a way of making things even more complicated than I can. Kind of funny, but so, but this is like just a standard thing, right? So he talks about a vibrational contribution to mixing. So again, this would be like basically like you have your icing model of a magnet with the arrows, and they're shaking. So you can think about up and down mixing. You can also think about like a vibrational mixing that drives the things to mix. Right, so you talk about this vibrational mixing. So you're gonna have the same format. So you're gonna end up with the kind of the same. All right, U prime's internal minus the vibrational, and you're just gonna add in this other term, whatever it is, configurational mixing, which is this is our original ln of G would give us our X ln X thing. This will give us X ln X, the original configurational mixing. The non-configurational entropic mixing is going to have to do with these states, a number of states like arrows pointing up, arrows pointing down, and then the numbers pointing up is A, numbers pointing down is B, and then ln of those gives you the basically this other term, right? Which is just going to be this eta thing, like right. So it's basically, this is just junk. He's just going to end up with a constant that has to do with how the arrows point when the temperature comes in, or vibrational contribution to mixing, which ends up giving you the same answer. It'll just give you the same thing that that equation, and then you can talk about a critical temperature for the magnetic demixing. In other words, thermally kind of the Curie temperature where this stuff flops out. You can think about it that way if you want. Right, so paramagnet to ferromagnet thing. I mean, if you so anyway, this could, you can see this could get, so this is one way to look at it, and this is another way to look at it. It's the same thing. You end up with the same equation. This is kind of temperature entropic, non-combinatorial entropy term added to the Hildebrandt thing. All right, so this, I mean, you could see this over and over again. Anytime you run into a problem, you're going to do things like that. So how does that look? So we have this plot of gamma, and then the ideal is when ln gamma is 0, and then you have these splaying for the positive is where you can get demix, where you can have a phase separation, and negatives where everything's going to be good, everything's mixes. And then if you do that, instead of plotting against composition, then plot that against temperature, right, for various values of the omega. So when omega is 0, you have 1 again. So it's the same thing. It's just ideal mixing. Gamma is 1. So activity equals the composition. So it's just the constant number. And if you have positive, then you have a possibility of demixing. But because you have this temperature thing, which is going to favor mixing, so positive means you're going to demix at some temperature, but as the temperature goes up, then you reach a point where boom, so there's that critical temperature, and then beyond that, it mixes, because beyond that, you have no, beyond that gamma would be negative. So you'd have, it would mix, right? So it's mixing or demixing. There's a critical temperature, but basically if you look at this functionality and temperature, there's this kind of swooping behavior, right? And the same thing, if you make this guy negative, so then you have normally everything mixes because the entropic term's always negative, and you add in a negative, so there's a negative free energy of mixing means it's going to mix. But if you throw in this term, this thing has a sign change, so that as you heat it up, this negative gamma becomes positive at some point, at a critical point. So that would be phase separation on heating, or an LCST phase behavior. Right. So by first by including this idea that you have an organizational aspect to mixing, which could happen all the time, right? In other words, if you mix two things, it's likely that something like that is going to happen, especially things that mix, or things that demix, because something's got to happen when they demix. So basically, it's likely there's a temperature thing involved in it. So then you would have these two cases where it could separate when you heat it, like this, when you have a negative omega, or it could separate when you cool it, like the normal circumstance when you have a positive omega. Right, so positive omega means that things that A likes A and B likes B. Right? In other words, A wants to be alone with A's and B wants to be alone with B's. The Israelis and the Palestinians. Then like the other case would be like the ideal world where A wants to be with B and then the world is at peace, So anyway, so that's your positive and negative omegas, right? And then you could have a temperature where that happens, right? So that's this magic temperature. That would be either phase separation on cooling, precipitation, or phase separation on heating, LCST, which we saw hopefully when I passed around those bottles. Like you'd warm it up and it would phase separate. So either one can happen. And particularly for these magnetic systems, that happens, so ferromagnetic, paramagnetic. And then also for the like a polymer UCSD, LCSD systems. That's kind of, and you write, because omega becomes omega by KT for chi, because it's G over KT that's dealt with, and you end up with chi as A and B by T. B by T would be enthalpic, even though it's got a temperature dependence, and A actually has a temperature dependence because you've taken out the temperature dependence. You divide it by it. So A is an entropic. And then you have these scenarios where A is positive, B is positive, positive, negative, negative, positive, and you get the possible outcomes. Always never mixes, always mixes, or phase separates on heating, or phase separates on cooling. Those are like your possible outcomes for a simple non-combinatorial entropy system, which is more or less the normal system. I mean, that's kind of like the things usually mix when you cool them down, but there's a critical temperature where they come out of solution. So this is the normal way, like sugar and water type thing. Right. So anyway, so that's that business. So that's one. So you can see like this simple thing about the X ln X thing, and then the adding in the entropy term, and then things can get more complicated depending on how much detail you want to put into it. And people have put a lot of detail into it, right? But still, even from a fundamental perspective, okay, this assumes that that the system's random. Okay, in other words, I put in an enthalpy term here, but it doesn't have any direction to it. Like it doesn't have, in other words, I'm not going to make a crystal this way. I'm not going to organize atoms into a crystal by this process, because these things are this is a random distribution. The way I got gamma here, the way I did that was by doing a statistical analysis based on probability. That's how I got this whole picture of having an average energy and how I could put that term in. Right. So there's an averaging of everything. So there's no way to build a crystal like that. You can't make a crystal doing that. All you can do is you can phase separate goo. It'll never be a crystal. It'll always be goo, right? So this thing starts to look like you could make a crystal, but it doesn't have like an organizational feature to it. In other words, there's no direction to it. In other words, the way this is maybe I drew it, so there is a direction, but there isn't a direction in the math of this. There's no vector involved in this thing. There's no pointing one direction or another, right? So things aren't always that way. So the signature of that is that you get a peak in scattering. In other words, if you do a diffraction, it means everything's organized with vectors. Like you have Bravais lattice and everything's pointing in certain directions, things have organized, right? So when they organize, there's a peak shows up when you do diffraction, say intensity versus angle. There's going to be a diffraction peak that shows up. So if you think the way to look at this business is you start with the dilute situation. So you have the intensity, say, divided by the concentration, because intensity is just going to go up with concentration, is proportional to it. You double the concentration, doubles the intensity diffracted. Right. So you have some curve for the dilute thing. So you have an object like that, that's what the curve looks like. Right, for whatever reason. Then as you increase the concentration, the things pack together. Right. So they're gonna start to kind of interact with each other. Right. So this is where so there's no enthalpic interaction here because they're too far apart. They can't see each other. So enthalpic is going to go as like 1 over R. You're too far apart. 1 over R is too large. When it's dilute, there's nothing there. Right. So you just get that curve. But as the things pack in together, right? And if it's a random arrangement, like we're talking about with this Hildebrandt parameter, right? Then if you plot intensity versus divided by, so you remove the fact that the intensity is going to increase with concentration, then you find out that this thing gets depleted, right? So what's happening there? Well, these things, say you look at if you look at like a fleece, like this stuff. So this is pretty concentrated. So you can't see any fiber in it. Like you can't see any one fiber. If it was dilute, you could see the one fiber. You could say there's a fiber, it's that long. It's like a centimeter long. Once you get up to beyond a centimeter where they're packed tighter than a centimeter, then you can't see that size anymore. So you screened out the structure above certain sizes. And that's got to do with how the fibers interact with each other, how that happens, right? So the Q is 1 over size. So there's some kind of cutoff size where you can't see anything anymore. At that point, you just see like the density of it, like just how dense is that fabric? Like, in other words, if it's denser, this would be a higher number. If it's less dense, it drops. That's just like, at this point, since 1 over size, this is like looking at the thing from a mile away and all you see is a shirt. That's it. You don't know what kind of shirt it is. You can see a shirt. You can say it's like how kind of transparent it is, but that's it. Right. So it turns out that number, 1 over that number is like the free energy, the enthalpy of mixing for the two things. So you can measure it by this kind of plotting intensity by concentration versus Q, and then see the dilute one and then see how this thing drops. The rate that this thing drops with concentration is the interaction energy between the things. That's the viral coefficient you can measure. So basically you can measure it that way. So this is a case where there's no organization of this thing. There's no direction to the interaction. So that's called a mean field. When the things can't see each other, that's called a mean field. It's a mean field interaction. So that's usually the first assumption when someone's going to do something. They say like, I'm going to assume a mean field. It means there's no direction. The interactions, you're ignoring all the directional features of it. Right. But if they're charged, like these are all positively charged or negatively charged things, then they repel each other, and there's a 1 over R squared, Q squared, whatever, Q squared by R squared dependence of that thing. Then basically there's a direction to it, so they're going to organize. They're going to basically try to make a hexagonal lattice or base center cubic lattice, like if they're spheres, right? So they're going to organize into a crystal, and that's going to lead to crystal planes or some preferred distance of separation at least, right? And that before you transform that, you're going to, in other words, the correlation function of this is going to have a peak in it, right? And that peak transform is going to be a peak in the scattering. So you do that, and you do I by concentration. You find out, oh, the reduced intensity actually spikes higher than the dilute one because I have a higher density of material there at that size, because that's the spacing for these things. That's where they prefer to space. And then there's a depletion. right? There's a depletion and then an increase. So there's a spike in it, there's a peak. Right? And that peak relates to this specific interaction. So you have mean field and specific, and the two things are totally not the same, right? But they can both, but still, if it's a shirt, right? If it was a fleece shirt or if it's a woven shirt, so a woven shirt would have like structure to the fibers that are laid down in a certain way, right? So basically that would have a diffraction pattern if you looked at that size scale. But if you look at the shirt from far away, you can't tell the fleece from the woven, right? They look exactly the same from far away. So far away, you still just see this kind of thermodynamic interaction. So the intercept, the I naught intercept of this thing is the same for the two. You get the same mixing, like second Viral coefficient from this thing for both, and it's the same number. Right? It's just that the organization of it is different in the two. This one is much more complex than this one. Like this one is fairly simple. That's what we've been doing. This one is going to be a matter of figuring out what's going on. Like how do you account for this? Because, well, we can talk, in this case, we can talk about a binary interaction like AA, BB, AB. That's a binary interaction. But in this case, you have to talk about AA, AAA, AAA. So you have to talk about ternary, quaternary. You have to talk about all the possible interactions, changing the interaction that you have just between the binary. So it isn't going to be just that, or it's just that won't make a crystal because, yeah, they can kind of organize on that direction, but every other direction it doesn't matter. But in this one, it matters, like every direction matters, right? So you can make a crystal from this, some kind of colloidal crystal or like an actual metallic crystal, right? When things interact in 3D and there's a connection between the directions and all in this thing. All right, so anyway, this is how right, so those are the two choices. So first, this is the mean field approach, right? So let me just talk about osmotic pressure here for a second. So mention this. This is kind of colloids, right? So like you're putting stuff into water. So it's basically like a protein or something, or a polymer or whatever. So if you have the solution and you have the stuff in it. So if you think about those things like as if they're a gas atom, then you say like there's a pressure and it's going to be like that, right? It's going to follow ideal gas law. So some kind of just putting, even if you just put like salt, right, into a solution, well, those atoms, those ions like bump against the walls and they create some kind of pressure. It's usually pi, capital pi. It's called osmotic pressure. And it's going to be related to the densities like the concentration and RT. Like that would be like the ideal case of this thing. So you can see this, like if you take, so you can take so this membrane is like you make a cellulose semi-permeable membrane that's not permeable to salt, but is permeable to water. And you can put your salt water here and your water there. So this pressure, this pi pressure, will be like the difference between these two columns. In other words, you can think of it like the water wants to dilute the salt water. It wants to go over there and dilute it. So it's driving the water up. So this is delta P. That's the pi. Pi is the difference between those two. So let's call it an osmometer. So you can measure it. You can measure this osmotic pressure. Right. So anyway, the idea is that you take that picture, and then this normally, if you want non-ideal mixing, you do like rho. So this would be like rho RT times 1 plus the second Viral coefficient plus the third Viral coefficient plus whatever. So usually you truncate it at the second Viral coefficient. And then you have an equation of state like that. That would be the Viral equation of state. So it's a power series expansion. And then you can take that and equate it to the van der Waal equation of state, like this guy. right? Which we had the binary, so rho squared times this attractive interaction between the salt things. And then the excluded volume of the salts would be, so that the excluded volume increases the pressure, or this thing reduces the pressure, the attraction. The pressure being the pressure of the things that are dissolved in the solution, right? So, right, and there's a pressure like this, so you can equate those two and you can solve for what this term, this A2 is. So the A2 is going to have units of volume, like the excluded volume. So if you didn't have enthalpic interactions, you had an ideal mixture, then A2 would just be the volume of the things that are mixing, whatever it is, NaCl that are mixing. And then when you add in this attractive interaction, then that like reduces this A2. Right, so it reduces the volume. It makes it so you have attraction between the things that makes it look like they have less volume. Then that, in other words, they're going to be less likely to, they take up less space when they attract each other. They reduce the pressure. That's going to reduce the pi. Right, so this, so you can write the A2 in terms of kind of familiar, somewhat familiar terms. Like just this expansion, A2 doesn't mean much, except that it's binary interaction. So the unary interaction, dilute 1, and then 2 interacting is A2, then 3 interacting would be A3. But if you want to just talk about A2 compared to the van der Waal, you find out it's a volume minus this kind of attraction between the things. So you can, that 1 over nu in this thing is basically A2. Like you can measure that A2 here in that measurement. There's other ways to measure it too. Like an osmometer will measure it. There's ways to measure it. This measurement though you can do on a solid object. Right? You can do this on mixing of any marbles or whatever you can do. Right? This, if you do it with an osmometer, you kind of need solutions. Anyway, so that's a mean field. That's basically this picture, like this picture of what's going on. That describes kind of how this thing's doing, right? That business. The other one, like this where you have correlations, then that gets into a whole like can of worms, right? So this is if you have correlations between the things. So if you had any hope of understanding how like metals crystallize, this is the route you would have to take. So this is a route people take when they're looking at like colloids, organizing, any kind of systems that are organizing. So this gets to be pretty messy, right? So idea is you have a correlation function. So it's going to be like one of these things. Like you have the correlation function, it's either G or H, right? And so you have exclusion of the central thing, and then you have like these kind of organizational layers. In other words, there's an exclusion, and the first layer of organization, and the second layer of organization, third, fourth, right? And that would transform into a peak in diffraction. You do a Fourier transform of that and get a peak. And this is the position from the center of the object to Leonard-Jones. This is like the radius of the object, sigma. So it's 1. It's kind of like your first. That's your radius. That's where you can't go inside of it if it's a hard core, and then you have the first kind of junction of the thing. So anyway, that's a correlation function. So anyway, that's what this HR is. So the HR, Ornstein Zernike, so Zernike won the Nobel Prize, but he didn't win it for this. You know, this is his most famous thing that he did. He won it for this confocal microscope. So he also invented the confocal microscope. I think Nobel Prize, it has to be something useful. This apparently isn't useful. So anyway, so this is the correlation function, and it's composed of the binary correlation function that you would use. So the mean field, like the one for this guy, the correlation function for that, then plus an integral of every possible combination of that binary correlation function with the actual correlation function. So this is imaginary because you're actually in a dense system where things are correlating, but this is what it would have been if it wasn't in a dense system, the binary interaction. And then there's an integral over the binary interactions so you're separated by a distance r prime, and then it's the binary interaction r minus r prime and integrate over all possible r prime. In other words, you integrate over all possible combinations of anything. So that's pretty messy. I mean, that's called a recursive function because the thing that you're trying to get is defined by the thing that you're trying to get. Means there's no answer unless you guess, unless you make a guess. Like you can't solve a recursive function unless you have, it's called a closure relationship, which means that you're guessing. You're guessing it's going to behave a certain way. Right, so this is commonly taken as like one of the major parts of understanding materials, I guess, especially colloids. It's kind of like the fundamental equations on the Zernike function. And then so this is complicated, but it gets like more and more complicated. So basically this Perkus-Yevik thing becomes really complicates it quite a bit. And then the simpler ways to kind of solve it, which is the Born-Green approach. And then then you can actually use this function and get back this this mean field behavior if you use a random phase approximation, which was also involved in a Nobel Prize. So it's kind of weird. I think the Nobel Prize has gotten to be like you can, in the old days you had to have a machine, and in the modern days it's like you can actually, like RPA is not a machine. It's also equally esoteric as the Zernike function. You know? So anyway, but they did win a Nobel Prize for that too. So anyway, so let's see. So I'm thinking maybe we should quit here, you know, and kind of come back to this next time. And maybe just skip over some of this stuff. Yeah, so anyway, yeah, why don't we just quit here for now? Because we got enough junk kind of floating around our heads that we can just kind of digest that, I think. And then next time I'll go through it's a Tuesday, I'll go through the homework and I'll kind of probably just go through a lot of these. What there is like an encyclopedia of different kind of ways to mess up that mixing function. So there's hundreds of different functions. So you can just kind of get a feel for it. Some of these are in some of the papers that we've looked at, you know, like the unifact thing was in one of the papers. So you can see these things get to be like so complicated. There's uniquac, unifac, there's like a bunch of different kind of mixing equations. You know, so you can just kind of get a feel for what, there's literally hundreds of them. So you just get a feel, and those are all for mean field stuff. So that the thing about the specific interactions is that there's only so much you can do with it. Like basically, because it's become so complicated, you can't go beyond like Ornstein-Zernike and some simple closure functions, and beyond that, it gets to be too hard to do. You know, so that's kind of where this goes. Like you get to a point where you can do. So then at that point, you just go into computer simulation, just feed it in. Like you feed in this equation with some closure, and you let it rip. So you don't bother trying to really understand it so much. So anyway, so yeah, so why don't we quit there? I could quit a little bit early because it's enough stuff here, I think. And then can go, you know, go from there. Any questions or anything? Stuff. All right.